My name is David Springer. I'm a senior software engineer here at Google. I work in the, just a minute, I just feel like Madonna. Okay. I work in the office in Boulder, Colorado in the US. What we do there is build the SDK for programming native client on the web. There's about 8 of us in the Boulder office. A lot of the native client programming also happens in Mountain View and Moscow, New York, and London. Today we'll do a quick overview of what the native client programming is all about, talk about the SDK itself, and go through a tutorial. I'm going to actually show you some code and write a small application today, and then we'll talk about what's coming up next. Okay, first of all, a little bit about the language I'm going to use. We call this environment native client, which is too big of a word, so we shorten it to NACL, which is, those of you who took chemistry in high school, this is sodium chloride, which is salt. So we have all kinds of bad puns on salt. We have salt and sea salt and pepper and things like that, and our project are named after seas, which are salty. Anyway, so what is NACL? And also, why should you even care about it? What we've produced is a way to write native code, so you can actually use a compiled language such as C or C++. We have others coming up, and run this native code in the browser. So we've developed a method of sandboxing and verifying the code that you compile so that we can produce native code that runs on the hardware, on your CPU, on the client computer, with the same safety and portability as JavaScript. So this gives you a programming environment for your favorite languages. C, C++. We're working on other languages too. I mean, you can imagine things like Objective-C and Go and Lua, Mono, C#. All these kinds of things are coming up online. We provide standard system libraries, so libc, libc++, things like that. We have all the kind of system interfaces you would expect in a POSIX-like environment, threading, memory management, that kind of stuff. We also provide a interface. It's a C, actually, an application binary interface to talk directly to the browser. So from your C++ code, you can script the DOM, you can talk to the browser and access all the devices that HTML5 gives you. So you saw in the keynote a lot of demonstrations of the 2D and 3D graphics and audio and things like that. All those same devices are available in the native client code to your C++ code with the same kind of security that you would have as if you were programming it directly in the browser. The idea is that you write the code once and it works wherever this environment is supported, on whatever browser, on whatever platform. So for example, today we support in Chrome, we support this runtime environment on Mac, Windows, Linux systems, ARM processors. We occasionally have it working in Firefox. We would like to see other browsers adopt it too. So what benefits do you get from NACL? Number one, there's no install at all. You get the full performance and native advantage of running code right on the client computer without having any installation process. So in the old days, when you used to have a plugin for a browser, let's say, the user would have to click some panel and go through a sequence of events to download something. There was all this awareness that there was actually a download. The plugin itself, of course, can do all kinds of nasty, malicious things because it's actually running natively, basically with full freedom and access to the hardware. Now with NACL, none of that happens. You build a native client module, a NACL module, and it's served as part of your web resources. So it just goes into your web app just the same way an image would. It's that easy. And we'll see all that, how that works later. You do get native performance. Because we have to write special validated code and it's not allowed to do things like jump out of certain address spaces and things like that, you don't get 100%, but you get pretty close. We're running, depending on the CPU and memory pressure your app has, is between 3% and we've seen up to 10% slower. But that's because the benefit you get then is full JavaScript security. So even though it's native code, it can't jump out into the computer at large and do bad things like erase a hard drive or anything like that. Another thing so obviously what this is good for is enhancing your current web application. So your web application today traditionally is written in some kind of markup, JavaScript combination. What this allows you to do is add also C++ code. So for example, what we're seeing now is people with a lot of legacy code that's already written in C and C++ can come into this environment pretty easily. So a couple of big applications that we're working with now are, for example, Earth and SketchUp and things like that have a huge C++ code base, and it would be very, very difficult, obviously, for them to just recast it into JavaScript. Another thing that we discovered this is really good for is, and I'll show an example of this later, doing things like encryption in the client only. So that means that clear data, clear text, for example, never flows across the wire. Everything across the wire is always encrypted. And we can, with the native client, with a NACL module, grab that encrypted data, decrypt it in the client, it never goes out to the web, and then produce the clear text just in the client and then re-encrypt it and send it back. Another thing that we've discovered this is really good for, we're doing some experimental software in Boulder, writing a little tiny 3D modeler, and we're using the Seagull libraries to do that. Seagull is a big geometric computing library that's developed all over Europe. It's all in C++. It's incredibly scary template code. And we've been able to basically port it. We just recompiled it. That's it. There was no extra special steps that we had to do. We just simply took the Seagull template library, recompiled it with our compilers, and presto, now it's ready for us to use to write this little 3D modeling tool. The reason we did that is because there's two reasons behind it. One is that it already was C++, so it was really easy just to recompile it. And the second thing is that when you start doing a lot of heavy computing and math, the JavaScript speed starts to really get in your way. If you're just chasing pointers and things like that through your data, JavaScript is totally fine. And JavaScript's really good at string processing. But when you come down to having to do a lot of heavy geometric computing and things like that, then you probably want to get into native code. And that's what we did here. Sandboxing is a big deal too. So you don't have to go through all the panel after panel of, are you sure you really want to install this, and do you trust this provider, et cetera, because native client is fully sandboxed. You know, I'll get into exactly how that works in a second, but basically when you're running a NACL module, you have two sandboxes. So there's the one that we provide you with the validated code, so you know that the native code can't do things like jump outside of the text segment and start running things in the data segment. We use segmented memory registers so that you can't get outside of a certain address space and things like that. We also block a lot of the, shall we say, I/O system calls, so that you can't just open a file on the hard drive. There's a very specific way of getting to files that live on the native platform. And it's the same, actually, exactly the same API that HTML5 has. We also provide that. You can't start a process, things like that. So you can't fork. We disallow that. And how that works in native client is that if those instructions are encountered, we just simply halt. So that if a malicious code comes in, then we do everything we can to just stop it. And I should point out that it's possible to write malicious native client code. We're not making that impossible. What we're doing is making it so that it won't run, which is different. The other sandbox, so that's the first sandbox, native client. And then the other sandbox is Chrome's sandbox as well. So we run within that. People with malicious intent or hackers have to not only get out of the native client sandbox, they also have to get out of the Chrome sandbox. So it's kind of doubly hard. So the penalty that you pay for this is we have to make code that is verifiable, which is generally a little bigger than if you just used platform native compilers, because we have to do things like put addresses on certain byte boundaries and things like that, and we have to, that causes a little extra padding. And there is a performance penalty because there's some runtime checking that we're doing while you're taking branches and jumps and things like that. We have to make sure that it's going to a valid address. So again, it depends on the application. If the application is generally very memory bound, you might see a little more performance degradation than if it's highly CPU bound. Highly CPU bound apps such as computation engines and things like that, the performance loss is very minimal. And as I said before, some system calls are just not allowed. So no making new processes, no direct access of the network. And these are obviously all things that are high security risks if we allowed it, so we just don't allow it. This is also a work in progress, so there's rough edges. And you'll see when I run my demos later on that well, they were working earlier, so let's just say that. So how does this make your life better? First of all, you can get native performance of the platform. And you saw earlier with the HTML5 stuff that HTML5 and JavaScript is getting really close to native performance already, especially in the area of 3D. I'll show some games later on written with native client. But with WebGL and 3D, if you have a lot of static data that doesn't need to interact geometrically with each other, generally speaking, you're getting perfectly fine performance staying entirely within HTML5 and WebGL. Where NACL comes into play is if you start doing a lot of computation on that geometry. So writing a 3D modeler, for example, is somewhere where you would say, I need to access the CPU and do a lot of heavy lifting in mathematics. You get platform independent multimedia, so that means that as with HTML5, you have a single API for all your 2D, 3D, and audio. And this is a write once, run everywhere kind of API. So there's no more having to specifically configure your graphics and your sound and so on and so forth. If you're used to writing client applications, then you've run into this already where, okay, you can deploy it on Windows and then 8 months later you've figured out how to do it on Mac and then again for Linux and whatever else you want to run on. This is no longer the case with native client. You write it once and we've done all the work to make it work on Windows and Mac and Linux and ARM and Chrome OS, et cetera, et cetera. You can write in your choice of language. So, and I'll show you later in one of my examples that it was easier for me to do string processing JavaScript and I want to do the computation in C++, not a problem. So I can, whatever language works best for the problem at hand, I can use that language. There are some low-level system services, threading, memory, that kind of stuff is all available, as if you were writing a POSIX application. And finally, you no longer have to put up these kinds of panels. And it says, you know, are you really sure you really want to install this kind of stuff? Because all of our code is fully sandboxed and it has the same level of safety as JavaScript. Okay, let me jump over here and start a demo. This is Unity. Has everybody heard of Unity? It's a game company. They have this engine. And what the Unity guys did, we worked with them to help port the Mono compiler and the Unity backend to native client. And let me get into this game. You can see this is actually really a game. I'm really clicking through all the... They didn't really give me a demo mode, which was sort of unfortunate. But anyways, what we did is we took there was 4 engineers, took us about a month to port the Mono compiler, which, you know, so the C# game development environment that Unity provides, and also their game engine. So, and you can tell this is all running in the browser, using all the OpenGL ES2 APIs. So start the game. So again, this is using the Unity player with and this is all OpenGL ES2. So actually part of that porting effort that we engaged in was mostly getting Unity to work with OpenGL ES2. The hard part wasn't really actually moving all the code base over. That basically was just a recompile. It was because their graphics needed to be ported to open. Okay, so here we go. I'm really bad at this game, but you can see. Here's Anakin Skywalker, and let's see if I can get this guy. Okay. Anyway, you can see this is okay, enough of that. All right. We've also ported a couple of other, well, I shouldn't say we, Unity's ported a couple other games. They have a little driving game, and I'll show it at the end too, this one thing they call Dark Unity, which is using a lot of heavy uses of the GPU. Okay, let's talk about the SDK. This is something that we're building out in Boulder, and the idea is this is what you as a developer of native client would get. We provide the C and C++ toolchain in the SDK. So this is a GCC front end. It works just as like you're used to with GCC if you compile C++ in native code. It's exactly the same thing. It's our version of GCC, so we've patched it so that it produces this validatable code. That's really the only difference between the two. Otherwise, the front end to GCC is exactly the same. We have all the standard GNU libraries, libc, libc++, et cetera, libm. Pepper is our, again, bad pun on salt, but it's the interface that you use to talk to the browser. So Pepper provides a way to script the DOM right from C++. The calls that you make look a lot like JavaScript. It's just, just slightly different language, but you can do all the same kinds of things. It provides an audio and 2D video interface. Again, all platform independent, so you write it once and it runs everywhere. Gives you OpenGL ES2 for 3D graphics, and you saw that with Unity stuff. And full JavaScript interoperability. So you can write C++ objects that can be accessed from JavaScript. And we'll show how to do that later on. In the SDK, you also get a bunch of sample code. So there's a hello world, there's a 2D graphics, and coming online we'll bring up 3D graphics as that comes available, and audio and things like that. So you have a lot of, there's some examples in there to copy and paste from. You build your application just like you would a client app. So if you're already used to building client applications using GCC, it's the same thing. It's not any different at all. We are working on integration into popular IDEs, Visual Studio, Eclipse, things like that, so that it becomes even easier to do that sort of thing. The tools run on whatever your platform of choice is. So I happen to program on a Mac. I use it on a Mac. We've got a couple guys that use Windows. We have others that use Linux. Just whatever you like. It runs on all that kind of stuff. The result of the SDK, there was when you build a NACL module, and again we'll show all this in the demos, but when you build a NACL module, you build a web resource. So in order to test it, of course, you have to run a little web server. And this is where it starts to get different from building client applications. So if you're used to building a client application, typically you build some executable .exe, or in a Mac a .app bundle, and then you just run it. Well, in this world, you don't do that. You actually have to build a whole web application which takes your NACL module and uses it as part of that and serves it. So really you are actually building a web app, but you have this native client component that sticks into it. And again, in my example, we'll show how to use all the markup in JavaScript and CSS. It all interoperates. Okay, so let's get into actually building the application. I'm going to build a small calculator. This is obviously incredibly contrived and very simple, and not the best use of native client. This is just for an example. Okay, what a web app looks like when it's NACL enabled is that you have a web application. It's my calculator. And the parts of it are underneath the hood that you have the markup in the JavaScript, just like you would any regular web app. Then there is the pepper layer that you talk to, which is how you interoperate between the C++ and the JavaScript. And that pepper layer is actually in the browser, right? So we've more or less built it into Chrome. That talks to the NACL sandbox, which then is running your actual NACL module. So there is a small runtime that comes built into Chrome that knows how to run these .nexe NACL modules. So the way we like to organize applications is that there are two basic parts. There's the application itself, which has all the markup and the JavaScript and CSS and so on. And then there's the NACL specific code, which is the C and C++. First step of the tutorial, I'm going to build just the GUI. So how I organize these things is very much along the, you've heard the model view presenter or model view controller patterns. They've been around for years. And that's exactly how these are built. Again, if you're used to building client applications, a lot of the big legacy client apps I've seen are often the UI programming and the model programming are kind of intertwined. In this world, that's really, really not possible. You really have to take those apart and build your GUI separate from your model. And that's how we're going to do this calculator. So step one is I'm just going to build all the web parts of it, which is the entire GUI. So I'm actually going to end up building a fairly completely functional application. It just won't actually do anything. So all the buttons are built in markup with CSS and so forth. There's a little piece of JavaScript in there to actually say, okay, now I have an expression and I want to calculate it. The JavaScript, I wrote JavaScript code to do the infix to postfix. So you know when you type in an expression like 9 plus 3, that's infix, and then I want to turn that into a postfix to make it easier to calculate. That's all string processing, and I'm much more comfortable doing string processing in JavaScript, so I just wrote it in JavaScript. And then we'll also go through and show how to actually connect in the NACL module without actually doing it. So the first step is, of course, I want to write some HTML code to write this calculator, right? So this is HTML code. It's not anything surprising. Here we've got the calculator itself, and these are just some of the buttons. And this is the CSS for a button in my calculator. The equals button is connected to the start calculate JavaScript, so that's here in the markup. Again, nothing really too surprising. I'm going to write a little JavaScript here, and the start calculate function first takes my infix expression that the user typed in, and it's going to convert it into postfix notation. And here's the JavaScript that, this is just the top of it, but basically it's going through the expression and parsing it. Again, it's all just straight ahead JavaScript string parsing, nothing surprising there. And then what it does is it talks to this calculator module. The calculator module is actually my C++ code, but it's represented in JavaScript as a JavaScript object. So as far as your web programming goes, this all just looks like another great big huge JavaScript object. And what I'm going to arrange is my C++ code will take as one of its parameters the callback or a closure that is also JavaScript. So what's going to happen in here, the flow will be that I type in an expression, I hit equals, it'll eventually call to the NACL module as we go through the steps of the tutorial. And then when it's done, the C++ will call back to JavaScript with the result. So that's what this is. Okay, let's take a look at that. Step 1 of the tutorial. So this is the calculator itself, and this is the code that you just saw. Again, there is no NACL module. So if I type in an expression here such as 8 plus 4 equals, it obviously doesn't do anything because there's no NACL module behind it to actually do the calculation yet. But again, it is fully purposed. It's a complete, the UI is all there. So I can do 8 times, I wonder if this will work, 5 plus 2 with brackets, and okay. All right, back to the next part. Now I'm going to add in the NACL module itself and actually do something with this expression. So we'll go through how to set it up and create the actual calculator instance itself, which is a C++ object, and call it from JavaScript. So there's a little setup code and some glue that has to happen in there, and we'll go through that. I'll write the actual calculate method, which is going to take that postfix expression and evaluate it and come up with a result. This is not really very heavy scientific computation here. Again, it's just an example. But essentially, this is the same thing that we're doing with the 3D modeling code, where we have this big geometric compute engine, and it's just literally taking data from the JavaScript, computing it, and then giving it back. Okay. So I'm going to program in C++ now. So on the chart here, I'm down now in my NACL module itself. So this all looks familiar to people who know C++. First thing I have to do is create an instance. This is the thing that actually connects to the browser. So earlier when I was talking about the Pepper API, this is what the Pepper API hooks to, is this calculator instance. And what I do is add a way for JavaScript to call into my C++. So there's this thing where I say, I wrote the call method, and what that is going to do, so that's the bridge from the browser into C++, and in that bridge I call my calculate method, which is there. And so the calculate method is actually where I'm going to do the final calculation in the C++ code. This is what the JavaScript looks like to call that. Again, the calculator module just looks like a JavaScript object, and it has a method called calculate on it, which I published from the C++ code. So C++ just says I have a string named calculate, and that's what I want you to use in JavaScript. Then JavaScript calls calculate with these two parameters. All right, back to the C++ code now. Here is the code that's actually doing the calculation. So what I do is take the first argument, which is the postfix notation expression. That's a huge JavaScript array full of strings. And you can see here that I'm getting the length property of the array. So everybody knows that a JavaScript array object has a length property built in, right? And so this is all I'm doing in C++. I'm going and accessing that property from the JavaScript object. That's what that get property does. Okay. So then I'm going to loop through the array, pulling off each string object in the array and process it. So I get operators plus and minus, I get numbers, things like that. Then when I've evaluated, so it's just a very simple postfix stack evaluator, nothing special there. Then what I'm going to do is use the pepper interface to push the value back to JavaScript. So here I'm back in the pepper stuff, and this is all I do is say, I look at the arguments I was given, and if I was given 2 arguments, I check to make sure that the second one is a JavaScript object, and then I simply invoke its default method, which is the function. If you give it a JavaScript function object, this is just a pepper thing. And I take the expression value, which is my double, turn it into a JavaScript object, and then send it back to the function object in the JavaScript code. And back into the JavaScript code, this is what it looks like. So this is going to get called. Okay, let's take a look at what that looks like. So first thing that happens is this. I wrote this panel. This is not something you have to have. But so it just tells me that it actually found a NACL module and loaded it. So I had compiled that. It's there. And it's just telling me that it worked. So now if I do my expression again, this is now going to actually use the NACL module to produce an answer. So there it is. I've gone now from, so if I do, whoops, clear this all. If I do 8 plus, no, I want 8. Let's see if this works. If my postfix evaluator really equals. So there, 8 times 4. So what's happened here is I've gone from JavaScript, I've done all the user interface stuff, handling all the button inputs. I produce an infix notation expression, used JavaScript to turn that into postfix, sent that into the NACL module in C++ code, which evaluated it in C++, produced an answer, and then sent that back to JavaScript. So now I've done the whole loop. Let's go through and add sound. So what I'm going to do, a couple things. First, I'm going to expose another method onto the JavaScript object and kind of show how that gets done a little bit better. And also show that we can add properties. So just as with your JavaScript objects, you can dynamically add properties. We can do the same thing here, and all that is exposed to the C++ code as well. So what I'm going to do is add a button sound property, and that's a Boolean. So I turn that on to say I want to hear the clicks, or I turn it off if I don't want to hear the clicks. And then I also add a click method so that as the buttons get pressed, it's going to call click, which should hopefully play the sound. Okay, so back into the C++ code now. What I'm going to do first is add the click method. And how I do that is, so these constants here, k calculate and k click, are strings. There's C++ string constants. And I add the click method. So that means that the browser knows if it encounters my calculator module, which is a NACO module, it will call has method if it sees click trying to be called on it. And here I return true if click is okay. Okay. The next thing I'm going to add is the button sound property, which again is just a string. So the browser, when it encounters JavaScript that says calculator module dot button sound, it's going to call into my C++ code and say, do you have this property named button sound? And here I return that, yes, I do. So it's really, it's that simple to add a property. When I set the property from JavaScript, so I say calculator module dot button sound equals true, it calls into, and this again is just, this is all Pepper API, it calls the set property with the value. And here I'm turning on a local Boolean variable that shadows that inside my C++ object, the play button sound. And this is the corresponding accessor. So when I want to see if play sound is turned on or not, I'm actually returning the Boolean value in my C++ object. I'm not shadowing this with JavaScript at all. So the value of that Boolean is always in my C++ code. And this is what it looks like in the JavaScript. So this is the click function. And you can see here I ask the calculator module, is sound turned on? And it will go through all that get property stuff I just showed you. And then if it is, I call the click method. Again, a little contrived. I mean, there's no reason that I would have to use JavaScript to discover if a Boolean is on or not in my C++ code. I could have just all done it in C++, but by way of example, that's what I'm doing. When the module first loads, I'm just going to default that sound is on. So I turn it on here with this call. Okay, the C++ code, the click method is here. And what I'm going to do is set this click pending flag to true. The reason I do that is because audio is all threaded. So the actual play of the sound happens on a different thread than the user interface thread. So here I'm doing kind of very cheap sort of semaphoring between threads. I just turn a Boolean on or off. I'm not taking any precautions to lock the data or use mutices or anything like that here. That's left as an exercise to the reader. Okay, so here's how we actually add the audio in. Using the Pepper API, again, what I'm going to do is inside of my calculator instance, part of its startup is that it gets an init method called on it from the browser. And inside that init method, I say I want a new audio device. And I give it my audio callback. So as the audio device runs in its thread, it's going to call this callback to actually play the audio. And I wrote a very, very simple callback, which is just a wrapper onto a method that's in my main object, this synthesized button click. And here's what that looks like. Really, really simple buffer copy code. It doesn't do very much. I'm not doing really any processing of the sound. What I did is I went out and found a WAV file on the internet of a really obnoxious click noise. And I'm simply copying the buffer from that into the audio playback buffer. And it gives me an offset of where to copy it and things like that. It's pretty straightforward. Okay, let's see how that works. Again, here's my little panel that says it loaded the Nexi module. Okay, so now if everything is working right, so now we have sound. Okay, we can use this stuff to write Chrome extensions as well. So those of you who've written Chrome extensions, you're doing exactly the same thing. There's nothing really special to do here. There's a couple little pieces of markup that you have to add in order to get the NACL module into a Chrome extension. Generally what we do is you write a background page for your Chrome extension, and this page is going to not do very much except load the NACL module. So that was the JSON of the manifest file you write that goes with every Chrome extension. And here is the background page, which shows, does the typical thing of showing the icon if you have one. And the other thing you do in the background page is this embed tag. And what it does is you provide this another manifest file which basically points at the .nexes that you built, which is your NACL module. So that's the thing that you add to the embed tag. This NACL attribute is something that we support in Chrome, and we're trying to get it out into the standards world so that all the other browsers will support it as well. And this is the little piece of JSON this is the manifest file that tells your Chrome extension where to find the NACL modules themselves. What goes on here is that this is obviously its native code, so you compile it for specific CPUs. We support x86 architecture, both 32 and 64-bit, and we support ARM. So part of your deployment process is to build run the compilers for x86 32, x86 64, and ARM, and you build 3 different .nexes. This manifest file, it figures out what the client is actually running on and then fetches the specific Nexi for that architecture. We're working on a unified bitstream format, so there's only one of these, and you won't have to actually compile for specific architectures unless you're using hand-rolled assembly code, and sometimes that's necessary in some of the bigger scientific stuff. Okay, so let's see if I can make this work. This is now a Chrome extension, and what this does is sends encrypted text over the wire. So again, as I mentioned earlier, this is where the data is never clear over the wire. This is local client decryption. So if I go up here and click the lock icon and type in my super secret password, AAA, it decrypts it on the client side. And now I see that. Again, this is never going over the internet. And to go back to the encrypted, I just simply reload the page, and I've got the encrypted text again, and so on. So, simple example. Okay. What's coming down the wire? We are working on a API we call sea salt, which is, again, another bad pun. And it's simplifying the interaction between JavaScript and C++. What you saw earlier, where I had the has method, add method, set property, get blah, 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 we've encapsulated all that into a set of very easy to use classes so that you simply write one line of code and we take care of all the rest for you. As well as things like marshalling. So those of you who work with JavaScript know that it's very, very loosely typed. It's dynamically bound. You have all these indeterminate types. C++ is exactly the opposite. It's very rigid. So what we've done is written a bunch of classes that help marshal between those two things. if you have a JavaScript object which has whatever in it, a string, but a C++ object that says, no, I really want that to be double, we do a lot of automatic marshalling and coercion and that kind of stuff. We actually use the ECMA specifications for that kind of coercion. And that's all built into those classes, as well as things like just simply saying, I want an image resource with this URL in your C++ code, just as you would in JavaScript. So the idea is to make C++ programming as easy as JavaScript is. We're adding the peer-to-peer networking support, full screen and mouse capture, and also coming later is IDE support for things like Visual Studio, so that if you are a Visual Studio programmer today, it will look very much like what you're used to, where you just simply write your code, you compile it, you attach a debugger, all that kind of stuff, and it just all works. And portable native client, as I alluded to, is this unified wire format, so that instead of having to, if you don't need specific features of a specific CPU, and your code will run generally well on anything, then you can write this one single format and have one Nexi module instead of having to load a bunch of different ones and cross-compile and so on. Okay, let me do one more demo, see if this will load up. So again, Dark Unity comes from the Unity folks, and what this demo shows is heavy, heavy use of GPU processing. It's all OpenGL ES2 standard, and what they did was write a lot of shaders to do all these kinds of special effects that hopefully it takes a little while. Yeah, okay. So the rain effect, I don't know if you can all see that very well, but there's, it looks beautiful on my screen. There's raindrops, that's all written in shaders. The lighting effects are all written in shaders. And again, this is all completely running in the browser. Okay, I think that we have time for some questions and things like that. There's this QR code that you guys, and I'm not sure that we're doing kind of a new thing for Prague, which is there's a web app that everybody can get, right? That does something, so, okay. All right, for that I'll open it up for questions and answers.
Is there a way that I can manage sockets like I would do with WebSockets, so I can receive notifications from a server without me calling for that information using making code?
That's coming up, yes. What we're going to do is, for example, in peer-to-peer networking, is the question was, let me get this right, is can I use something like WebSockets from within C++ code? And the answer is yes, you will be able to. Yeah. Yes?
Do I understand correctly that you have to have for everything this native API? So whatever you don't write the API for, I cannot use the solution.
That's about right. The question was, I'm sorry, the question was, you have to use this native API to write native client code. Is that correct? Yeah, so that's, yes, generally speaking, yes, that's what you have to do. We do provide all the POSIX APIs, so open, close, read, write, things like that onto the special file system, and all the pthreads APIs are there, and any standard libraries, so libm is all there, sine, cosine, all that kind of stuff. 3D is OpenGL ES2, yes. Yeah. Yes?
For table native client binaries, is it something like bytecode which is compiled to the native code? Because I do have idea how you can have one machine code which will run on Intel processor and let's say ARM processor, so maybe I can probably get the slide.
So the question is, how do we do portable native client code? How do we make it work? It's an LLVM bit stream, and then instead of just validating in the runtime, we translate and validate. in the run on the client code. So the actual bits going over the wire are all the same LLVM bit format, but then it's when it hits the client side, we translate and validate. Today we just validate. This stuff is all available on the websites that there. So there are white papers, and there are all the research papers and things like that that talk in much more detail on these websites. Yes.
What about sandboxing the native client module in the page when I want, like, if I have like, I don't want it to see the whole page, but just my JavaScript object. Does it work like this, or is it possible to just, you know, the problem of mashups? If I want like load different native client modules and separate them on the same page.
Okay, so I think the question is there a way for native client modules to not see the whole DOM, right? No, there isn't. It's just like writing it's a JavaScript object in the DOM. So you can get the window object, you can get the document object.
No, this is big problem with JavaScript libraries. You, for example, have
Yeah.
code from different sources, and you want to sandbox them on one page.
Right.
Big problem.
Yeah, it's. I understand. We follow the same model that JavaScript has, and there's no sandboxing that I'm aware of to say you're not allowed to have the window object.
To me, it looks like you have access to whole DOM from the native client module.
That's correct. You have access to the whole DOM from the native client module. That is correct. You can get the window object or the document object and script it. Yeah, okay. All right, I think that's it. I think we're, yes, one more? The question is, are we going to implement NACL for other browsers besides Chrome? We really want to see that happen. We have, in our shop, we have a Firefox plugin, but we don't really maintain it. What I would really like to see is these other browser manufacturers really adopt native clients so that they write the implementation and own it and maintain it, so that it's not all from Google. I don't want a world where everything comes from Google. All right, thank you very much for coming, and that's it. I guess other questions, I'll be up here.